This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is exergy of a gas. In this example, we've got a cylinder of CO2. We're told it's at 300 Kelvin and 1 megapascal. That's about 10 atmospheres. And it contains 0.01 kilograms of gas. We're asked to find the exergy when the surroundings are 300 K and 1 bar. Now here's a definition of the exergy for a closed system, which is appropriate for a gas in a tank. And the exergy is a comparison between the state of the gas, identified here by internal energy, volume, and entropy, with values at the dead state. So we're comparing to U0 to V0 and S0. Those are the dead state. U0, V0, and S0 are values from the dead state. And the dead state is defined as a sort of a thought experiment, would be if the system were allowed to become in equilibrium with the surroundings at P0 and T0. So that's our comparison. Now in this particular case, it's gas sitting stationary in a tank, so there's no kinetic energy, and it's not moving, so the potential energy is 0. The tank temperature and the surrounding temperatures are the same, so the internal energy drops out. So we have left just the comparison between the volume and the entropy. So those are the quantities we need. So let's go after the volume difference here, V minus V0. Using the gas law, we can write V as MRT over P, and we can write V0 as MRT0 over P0. Let me recopy this. Because the temperatures are equal, I'm going to write this as MRT0 times 1 over P minus 1 over P0. Let's put some numbers in. V minus V0 is going to be 0.01 kilogram times the gas constant. I'm going to write that as 8314. That's in joules per kilomole per Kelvin. And I need to divide that by 44. That's molecular weight. 44 kilograms per kilomole for carbon dioxide. Then I need the temperature of the surroundings. Oops. Temperature of the surroundings is 300 K. And I need the pressures. The tank is at 1 megapascals, that's 10 to the 6th pascals. And the surroundings is a bar, that's 10 to the 5th pascals. Let's check the units on that. I've got kilograms here. I've got joules per kilogram per Kelvin here. I've got kelvins here, and I've got upside down pascals, which would be meters squared per Newton. Kelvins go out, kilograms go out. So I have left a joule times meters squared per Newton, but a joule is a Newton meter. So I've got Newton meter, meters squared per Newton, so I get meters cubed. That is indeed volume. Let me crunch the number here. The 10 to the 6th is bigger than 10 to the 5th, so the invert is smaller, so I get a minus sign. It's minus 0.00510 meters cubed. All right, that takes care of the volume term. Let me go down and look at the entropy term next. For specific heat equals constant theory plus ideal gas, we developed a relationship for an entropy change of an ideal gas to be the mass times a specific heat times a log of the temperature ratio minus the gas constant times the log of a pressure ratio. The temperature ratio, T over T0, is 1, and the log of 1 is 0, so that term is gone. So let's put some numbers in here. We've got the mass, 0.01 kilogram. We've got R, well, minus fine, minus R. I'm going to put R in as 8314 over 44 as before, times the log of the pressure ratio. The system pressure is 10 to the 6th, and the surrounding pressure is 10 to the 5th. And let's look at the units. We've got kilograms. We've got joules per kilogram per Kelvin, and this one has no units, so the units are just joules per Kelvin. So my entropy difference, S minus S0, when I crunch the numbers, I get a minus sign there. Minus, I get 4.351, and it's joules per Kelvin. That's the units of entropy. All right, now we have everything we need to compute the exergy using this relationship here. So the exergy for the gas in the tank is going to be the surrounding pressure, 10 to the 5th newtons per meter squared, times the volume change, which was minus 0.0051 meters cubed, minus the surrounding temperature, 300 K, times the entropy change, minus 4.351 joules per Kelvin. Now the kelvins drop out, so we get joules. And the value is, let me write this in two pieces. Value is, the first piece is minus 510, and the second piece is plus 1305. So there's competing effects here. And when we make that subtraction, we get plus 795.3 joules. Now the important observation, that's the response, that's the exergy. But the important observation is that if the exergy is positive, then useful work is possible. And the size of the exergy tells us how much useful work. Now, what is gas in a tank used for? CO2 in a tank is often used as a propellant. For example, for a BB gun or a pellet gun. But another use, at my school anyway, is for the hot dog shooter at the football games. I had a conversation several years ago with the meat seller that shoots the hot dogs to the students, and he said, the students are high up in the stands, how can I shoot this thing farther? And my first thought was, could he use a lighter gas? Because both terms in this expression are multiplied by the gas constant. A lighter gas that's safe to use, it's not cheap, but it's safe, is helium with molecular weight of 4. And the gas constant for this gas is 8314 divided by 4 instead of 44, which would be 11 times higher than for CO2. So that's one way to get a very exciting hot dog shooter would be use a lighter gas. The lightest gas of all, of course, is hydrogen. But since it is flammable, it's not something that you probably want to use. Although that could make it more exciting. M equals 2, so it could be more powerful. Yet you can make hydrogen has been used for the fastest possible field piece or a super gun. But I'll leave that I'll leave that exploration to you. Let's recap. We're asked to find the exergy of gas in a tank. We're looking at carbon dioxide at certain conditions. Whenever we look at exergy, it's a comparison between the known state, U, V, and S, and the dead state, U, U0, V0, and S0. And the dead state is defined as the system in equilibrium with the surroundings. So exergy always requires that we know the surroundings and make a comparison with that. We used the gas law to find the volume change. We used specific heat equals constant theory to find the entropy change. We found that the exergy was positive. So that means that useful work is possible for this system. And the size of the exergy tells us the amount of useful work that's possible. That's one of the uses of exergy. And if you remember that the size of the exergy tells us the amount of useful work, then all will be well.